2, we're going to be looking at the atomic models throughout history. It's one of our state standards. We need to look at how the atomic model was developed throughout time. So we're going to look at the very earliest model, and that was developed by Democritus. And the word atom actually means smallest particle of an element that retains its identity. So there are smaller pieces like electrons and protons, neutrons, but by themselves they don't retain the chemical and physical properties of that particular element. So Democritus was a long time ago, 460, 370 BC, and he just said that the atom was indivisible. In other words, you can't cut it down any further and still have the element that you had. It's indestructible. As far as what he would maybe think of an atom, just a plain circle. That's it. Just that was the atom. Didn't go into any detail about anything smaller than that. And then we jump ahead quite a ways to John Dalton. And he had several parts to his theory about atoms. He said that all elements are made from atoms and that they are indivisible and indestructible, so he agreed with Democritus, but then he added onto it that all atoms of the same element are exactly alike. He said that they have the same mass. That's a key one to remember, because as we learn more about the atoms, we'll actually prove John Dalton wrong with this number 2 here. He also said that compounds are formed by joining 2 or more elements. We know that already, the definition of a compound. And he also said that in any compound, the atoms have to have a certain whole number ratio. So for instance, like in water, we have 2 hydrogens for 1 oxygen, or in salt, you have 1 sodium for 1 chlorine. So they have to be in a whole number ratio. You can't have half of an atom. Some things that Dalton's model did not account for: he did not go into any detail at all about protons, neutrons, and electrons. So his model would look pretty much very similar to Democritus. And let's see, no nuclear reactions, so he had no nucleus at all. And he did not account for isotopes, and this is where we'll look at isotopes more another day. But number 2, when he said that all atoms have the exact same mass, they do not, and that is because of isotopes. So his model, though, was the first one to be backed by some scientific evidence. It wasn't completely accurate. We've definitely developed it, but his is the first one who had some evidence with it. Then our next 2 scientists here, we're actually going to look at some of the experiments that they conducted, because now we're going to get into some subatomic particles, so smaller than the atom. J.J. Thomson, he discovered the electrons. Definitely a test question. You need to know that. And he used a cathode ray tube and a magnet in order to discover these. And so this is what his experiment would look like. Here's our cathode ray tube. This is a tube that has gas inside of it. And when you have it hooked up to a voltage source, naturally the negative side will be attracted to the positive side. And so when you pass an electric current through this cathode ray tube, you're going to get a beam of light that appears, showing up from the negative side to the positive side. And we're actually going to be able to see some cathode ray tubes and some of the colors that they give off when you hook electricity up to them. So now what he did is he added a field around it. So you can see this positive side here and this negative side here. He had this magnet, and he added an electric field around it. And he noticed that when he put the magnet over here, that the beam kind of changed its direction. And so he knew that this particular beam had to be negative because it was attracted to the positive side. Hence, we come up with electrons, which are negative. Now, his model is nicknamed the plum pudding model. He was from Britain, and in plum pudding, they have this pudding here that he considered to be all positive mass. He did not come up with protons. So he just said everything that these negative electrons are sitting in is positive material, and there are tiny little negative electrons that are just scattered throughout our positive mass. And so that's our plum pudding model. Plum pudding is pudding with like raisins, I believe, kind of scattered throughout in it. So we definitely are a step up, because we do have the mention of positive particles, we have the mention of negative particles, specifically electrons. So the last scientist that we're going to look at today, his name is Ernest Rutherford, And him and Thomson actually worked for a period of time together. His experiment is called the gold foil experiment. I guarantee this is an essay question on your test. You need to be able to describe his experiment and how he conducted it. So we need to know a little bit about it. First of all, we're going to see a picture here in a second. We have this beam of light, particularly they were alpha particles. Alpha particles are positively charged. And so he is going to shoot these positively charged particles at a piece of gold foil, hence the gold foil experiment. And this is, you can see in the picture, this is his results. So he had a ring of metal around the gold foil, and the gold foil, when the positive particles hit it, the beam of light, some went behind it and hit the metal here in the back. Some deflected and even bounced almost kind of straight back toward the ray itself. So here was Rutherford's kind of hypothesis. He expected that these positive particles were going to pass straight through the gold foil, not changing direction or not changing direction very much. And the reason that he thought that was because of Thomson's model. Thomson had these positive charges that were kind of evenly spread out. And so when positive and positive hit each other, they don't like each other, they repel each other. But since Thomson's positive particles were evenly distributed, Rutherford didn't believe that those positive particles would stop the alpha particles that he was shooting. So this is what he expected to happen. He expected the beam to pass straight through. And again, because you have this whole blue ball here being positive, you're going to see the beam of light as it's being shot through, not very much change in direction. So the positive blue ball mass doesn't really affect the alpha particles. But that's not what he got. So here is what happened when he shot the positive alpha particles. He actually had the beam kind of like what he expected here, but then they deflected quite a bit more, and even more so, almost bouncing kind of straight back. So the alpha particles did not follow his expectation. They went straight through, and others bounced off at really large angles. So here's how he explained that. I just mentioned that when positive hits positive, they don't like each other. So Rutherford said the whole entire mass of this atom is not positive. The positive part is actually concentrated in the middle, and it's a very small positive mass. And so he said really the atom's pretty much empty space. You can see in this picture not a lot going on here except for this little positive center. He also said that there is a small, dense, positive piece at the center. This is called the nucleus, we know now. And alpha particles are deflected because when they come in contact with this very concentrated positive nucleus, they deflected in all sorts of crazy directions. And so we get this. Okay, we have some passing straight through because they were further away from the nucleus. The ones that are hitting closer to the nucleus are bouncing straight back, bouncing off at very large angles. So to sum up Rutherford's model and to finish this up for today, the atom is mostly empty space. He also said that the positive charge is not the whole circle, but it's just the positive center. That's all the positive particles are located right in the center. He did come up with the word nucleus. So the nucleus is the center of our atom. It is made up of protons, which are positive, and neutrons, which have no charge. And protons and neutrons are in the nucleus, and then he didn't change electrons. He said that the electrons are around the nucleus. They're in that empty space. So this was an improvement on Thomson's model. It's better. We now have a nucleus. We now have the protons in the nucleus and the electrons around it. But as we look later, we will find that even Rutherford's model had some issues, and that we will expand upon it and make this model even better later in